Now let us study the geometric progression, which is also called as GP. It is a sequence in which the ratio of the consecutive terms is constant. So if you compare this with the arithmetic progression, in AP we had the difference of consecutive terms constant, but here it is the ratio of consecutive terms that is required to be constant. So if we have the terms as T1, T2, T3, T4 and so on up to say Tn, we want the ratio of each consecutive terms as same, that is we denote it by say R as the common ratio. So it's nothing but whenever we multiply T1 with R we get T2, we multiply T2 with R we get T3 and so on. Alright, so that is the definition of a GP. Typically here also we denote the first term with A and the common ratio with R. Alright. So now let's move ahead and see how can we write any general term of a GP, that is any nth term of a GP. So as we have seen, as per convention, the first term is A. So the second term will be nothing but the first term multiplied with the common ratio R. Now moving further, we have third term will be AR multiplied with R, that gives us AR square. One more example, T4 is nothing but AR cube. So now looking at the pattern, we can easily say that the nth term will be given by A into R raised to n minus 1, because whatever is the term number, the power of R is 1 less than that. So therefore when it is n, the power of R should be n minus 1. Alright. So therefore this is the formula for nth term of a GP. Now let's go ahead and see how to find the sum of first n terms of a GP. Alright. So that means, suppose let's denote that sum as first term is A plus second term is AR plus third term is AR square and so on up to the last term will be A into R raised to n minus 1. Right. Now to get the sum we follow a very specific approach. Okay. What do we do is we multiply this equation, let's call this equation as say equation number 1. Now we multiply this equation throughout by R. Alright, and let's see what happens. So on left hand side we will have R times S is equal to A will become AR on multiplication plus we will have AR square. Right, AR gets changed to AR square after multiplying with R and so on. Similarly next will be AR cube, and lastly the last term will become A into R raised to n. Right, this is equation number 2. Alright. Now what do we do is we subtract first equation from the second equation. So that means we do equation 2 minus 1, and let's see what does this give. So that means we have RS minus S on left hand side. Now whenever we subtract first from the second, now looking at the RHS, AR will get cancelled, AR square will get cancelled, similarly AR cube will get cancelled and so on up to this last term AR raised to n minus 1 will get cancelled. So the only terms that remain is AR raised to n on right hand side, and from that this one A which was in the beginning, that will get subtracted. Right, all the terms will get cancelled in between. So therefore taking S common we have R minus 1 on left hand side, and on the right hand side taking A common we have R raised to n minus 1. So which in turn gives us S is equal to A into bracket R raised to n minus 1 whole upon R minus 1. So this is the formula to calculate the sum of first n terms in a given GP. Now here we had subtracted first equation from second equation. We could have also done the other way around, that is we could have subtracted second from first. So in that case the formula will become, instead of r raised to n minus 1, we'll have 1 minus r raised to n whole divided by 1 minus r, right, which is nothing but equivalent to the first form only. So these are really not two different formulae but one and the same. Alright. Now let's go ahead and see the further topic, that is how the properties of geometric progressions are affected whenever we do some operation on each term. So the first property is, if each term of a GP is multiplied or divided with a constant, then the resulting sequence is also a GP. Then secondly, the product or division of two GPs is also a GP only. And the third is, if x1, x2, x3 and so on etc. are in GP where xi is greater than 0, that means each of the term in this sequence is greater than 0, then log of each term, that is log of x1, log of x2, log of x3 and so on, will be in AP. So that means if certain terms are in GP, then their logarithms will be in AP, assuming the logs exist. Okay, so we also make use of these properties wherever they are applicable. It will be important to note that in property 1, it is only multiplication or division which is allowed, because GP involves the ratio to be constant. So hence if we have addition or subtraction, then the resulting sequence will not be a GP. Let's go ahead and see how to assume the unknown consecutive terms in a GP. So like we have in AP, if say 3 terms are in AP and they are to be assumed with variables. So similarly here also let's consider that there are 3 terms in GP and we have to assume them. So what is a good way to assume them? First is A upon R, then second term is A and the third term is AR. Now this is a slightly better way to assume the 3 terms rather than A, AR and AR square. Alright, so rather than this is a better way. Of course it is not the second way which we saw is not a wrong one, but in some cases the method shown here works better and is more convenient. Alright, so that's the way we assume the terms. Now here the example we saw is for only the 3 terms, right? But what happens if there are more than 3 terms? Say for example there are 4 terms or 6 terms, that is even number of terms. So in that case, how do we assume? Now this is also very much analogous to what we did in arithmetic progression. So here the terms to be assumed are A upon R cube, A upon R, AR and AR cube. So now here you see from term to term, the common ratio is not just R, but it is R square. So in this way we assume the unknown terms in geometric progression. Now based on this we will see some of the examples.